The soil sample was collected in a remote Indonesian jungle by a Christian missionary. A few grams of dirt scooped into a sample bag and shipped to the United States. Little did anyone know what those few grams would contain. A drug, so special that its Chinese characters literally mean the antibiotic of the ages. It has been nearly 70 years since its market entry. In today's video, I want to pay tribute to an iconic compound, the unique, mysterious, infuriating, but life-saving antibiotic Vancomycin. For over 3 decades, our drug of last resort. Staphylococcus aureus, or staph as I shall call it, is a spherical bacteria that appears in bunches. They remind me of grapes, but like murder grapes. Staph has long been a special thorn in the medical world. For the purposes of our story, there are 2 things we need to know about staph. First, it is a gram-positive bacteria. The term has a technical definition, but it means staph has a thick, almost mesh-like cell wall made from, among other things, peptidoglycan, a big molecule. The second thing to know about staph is that it sucks. When people are down on their luck, it is among the first to come and kick them, causing opportunistic infections that can get very serious, particularly in hospitals. Today, it is one of the leading causes of death by infection. In 2017, the CDC estimated staph to be responsible for 119,247 hospitalizations and 19,832 deaths in the United States. A staph infection is no joke. What makes this joke even less funny is that staph grows and changes fast. It picks up some antibiotic-resistant gene somewhere, and then before you know it, spreads like wildfire. And now all the staph bugs are resistant. Penicillin first entered the hospitals in 1941, immediately changing the prognoses of such infections. But almost as soon as physicians started using penicillin, staph started becoming resistant to it. I hate it when they do that. The first paper detailing this phenomenon was published in 1942, literally a year into the so-called penicillin revolution. Penicillin belongs to a class of drugs called beta-lactams, and these work by inhibiting an enzyme that staph uses to produce its peptidoglycan cell walls. The defective wall then bursts like a wet paper bag, spilling the bug's guts everywhere. The best part is that human cells do not have these types of cell walls, so the drug leaves them relatively untouched. However, this enzyme-centric mechanism is vulnerable to workarounds. If penicillin is metaphorically like the fake key that jams up the lock, then staph or other bacteria can just break that fake key or change the lock. That is what staph did. They produced this enzyme called penicillinase that disabled the penicillin antibiotic. This gene spread fast, and by the 1950s, penicillin resistance was widespread. This sent pharmaceutical firms scurrying for new antibiotics, targeting a phylum of soil bacteria called the actinomycetes. Programs were set up to collect samples from the farthest ranges of the world. Participating in one such program was the Reverend William M. Bowe of the Christian and Missionary Alliance of New York City. The pharmaceutical firm Eli Lilly & Co. had a pre-existing, rather informal arrangement with the missionary organization to collect soil samples, and this dated to Bowe's colleague William W. Conley. Conley sent back a few samples while in Indonesia. They did not produce any new antibiotics, though one did have the already discovered antibiotic chloromycetin, but the microbial landscape looked quite unique, which was encouraging. So Edmund Kornfeld, an Eli Lilly chemist, wrote to Conley in a letter advising to really go, quote, off the beaten track, away from the towns and villages, end quote. But Conley had to return to the United States, so he handed the vials to Bowe. Bowe knew nothing about antibiotics, but nevertheless diligently picked up the task. Months later, in February 1953, he sent back a crate of soils to Eli Lilly via airmail. And he wrote in a letter that the samples were collected during 1952 in the deep jungles of Tengeng, Borneo. and he wrote that he hoped that they might be of use. By the way, I want to call out Donald J. McGraw's 1974 thesis, The Antibiotic Discovery Era, as a crucial source for this part of the video. McGraw somehow got unprecedented access to Eli Lilly's corporate records and workers. Read the thesis, it's amazing. Once the crate arrived, an Eli Lilly lab technician took the samples and grew colonies of the bacteria inside to test for antimicrobial activity. This used to be done with an agar plate, but by 1953 this had been replaced with a liquid broth method. The samples are put into warm liquid broths, shaken occasionally for aeration. The bacteria grow inside and secrete chemicals into the broth, and that broth is then tested for antimicrobial activity. In June 1953, a research scientist named Marvin Hohen notices that something is up with tube culture M4305865, the number indicating that it was the 5,865th culture done in the whole program. Per Eli Lilly procedure, Hohen then does a second screening test called paper chromatography to identify whether the antimicrobial substance in M4305865 is actually new. Performed on June 18, 1953, it confirms as such to Hohen. Even so, at this point, everyone was just going through the motions. 05865 was just another drug candidate. Some time would pass before they realized that they were dealing with something truly special in that broth. One of the first goals the Lilly team had with 05865 was figuring out how to scale production. No point in testing a drug's antimicrobial tendencies if you can't manufacture it. And this meant growing the bacteria, now known as Amycalopsis orientalis, and then extracting the antibiotic it produced and purifying the mixture. Through trial and error, Lilly scientists eventually discovered a recipe for a liquid medium that the bacteria best grew in. The various recipes, tweaks, contain nutritious but ordinary things like milk derivatives and sugars. But it always amuses me to know that the core ingredient was Brer Rabbit molasses. I wonder how it tastes. Lilly at first struggled to purify the drug. The first process employed a chemical called picric acid, but the yellowish picric acid can, in certain situations, literally explode. They used it in World War I to blow stuff up. So this forced a switch, and the new method did not perform as well, resulting in the first batches being just 30% pure. The dirty brown concoction earned the moniker Mississippi Mud. This impurity causes toxicity issues. In June 1954, Lilly tried the drug on a human patient for the first time, and that patient experienced pain upon injection, their veins immediately inflamed. In January 1955, it happened again in a second set of patients. This was not seen in earlier animal trials and remained a lingering, if rather unjustified, concern for many years thereafter. By mid-1954, it gradually dawned that vancomycin was no ordinary antibiotic, despite these toxicity issues. It killed a broad range of bacteria, including multiple staph variants. But most interestingly, bacteria seemed to have an unusually difficult time developing a resistance to it. The first sign of this was that the amount of antibiotic needed to kill bacteria was just a tiny bit more than the amount needed to stop them from multiplying. Researchers believe that this gives the bacteria less chance to evolve resistance. Another test exposed staph to a drug many times and noted how fast it developed resistance. After 20 exposures, staph resistance to penicillin had grown 131,056 times over, but to 05865, just 4 to 8 times. These findings dramatically raised the drug's profile inside the company. Then, when the drug started to be used on human patients, stories of its near miraculous nature, barring the apparent toxicity, rapidly circulated. One case from early 1955 relates a patient at Lilly Research Clinic with a post-surgery staph infection in his foot. Existing antibiotics weren't working, either in huge doses or combination, and the doctors recommended amputation. They called Lilly's clinical investigator Richard Griffith, who later writes, "The foot and the lower leg were tremendously swollen and indurated, and there were several sinuses draining pus. We told him about this new antibiotic, and he said, just as any of us would have said, anything that might save my foot." The case's severity warranted a higher dose of 05865 than what Griffith recalled he wanted, but it worked. He continued, "In 5 days he was getting 100 milligrams every 8 hours and he felt better. Heat was disappearing out of his foot. His white cell count was dropping and the exudate from his wound was less. During the next 7 days, the staphylococci disappeared from the wound." And then they ran out of doses. Fortunately, the guy pulled through and was discharged 2 months later with an intact foot. Stories like this rapidly piled up. The rare times the drug failed, there were attenuating circumstances. One such case saw a guy get kicked by a horse and develop liver abscesses. The drug eliminated a staph infection in his blood, but the bacteria survived inside a grapefruit-sized clot that the drug couldn't access. And then the bacteria eventually then got to his heart. Geez, these mortality reports are really depressing. On March 1955, Lilly set up a higher-level committee to develop the drug as a product, meaning to finalize drug production techniques, dosing, formal clinical studies, and more. Also, naming. The first suggested name for 05685 emerged in May 1955, Tenggasin, since the soil sample was collected in the forests of Tenggeng, Borneo, and this one unfortunately did not stick. Then in September 1955, the name Vancomycin emerged on the record. It is often said to have been derived from the word vanquish, but that is not quite true. The actual root, as sourced from the actual Eli Lilly document, was the Latin word vanesco, which means to vanish or disappear. Mycin is simply the suffix suggested by the American Society for Microbiology for all products derived from Actinomycetes bacteria. Why vanesco? Nobody recalls. Nobody also recalls who came up with this rather uninformative name. Probably someone from Eli Lilly's marketing department, as that was the procedure at the time. But anyway, this one stuck. Eli Lilly did surprisingly little work on vancomycin's chemical structure and mechanism of action. They even noted this in their records at the time. About all that was done was a basic elemental analysis that showed that 1. Vancomycin was a big molecule, unlike any antibiotic ever before seen, and 2. Some toxicity was to be expected. This was due to the perceived urgency of the antibiotic resistance situation. They were rushing to get this new drug to a desperate market. They knew it worked, and that it worked by somehow inhibiting cell wall formation, like penicillin, but in some way different. What that mechanism was, Eli Lilly left for the academics. Years later, we know now that vancomycin indeed works by messing with the bacteria's cell wall construction process, same as penicillin. But rather than attacking the enzyme stacking the bricks to make the bacterial cell wall, it attacks the bricks themselves. Vancomycin binds tightly to a small dipeptide called D-alanyl D-alanine, which sits at the end of a peptoglycan precursor unit, so kind of like a little tail. During the cell wall formation process, this tail ensures that the precursor fits snugly into the metaphorical quote-unquote brick wall. Vancomycin's own binding, anchored by 5 simultaneous hydrogen bonds plus van der Waals forces, is far more snug. The result is a monstrosity of a precursor quote-unquote brick that is too big and bulky for practical use. The cell wall falls apart, and the bug spills its guts like a 3 a.m. drunkard. It's so genius, and I cannot imagine how they ever evolved it. Researchers, too, had never seen anything like it before, making vancomycin the first of a new type of antibiotic known as the glycopeptides. A second member was isolated a year later, ristocetin, briefly used in the 1950s but eventually withdrawn because it caused life-threatening blood clots or bleeding complications. But a few others were discovered in the 1970s. The drug's first clinical trials focused on fighting penicillin-resistant staph and were small in scope. But word of vancomycin's effectiveness quickly got around, which brought more potential patient cases. Considering the penicillin resistance crisis, the U.S. Food and Drug Administration fast-tracked the drug and approved it in 1958 as a first-line treatment for staph infections. However, soon after that, in 1960, methicillin was made available. This is a semi-synthetic antibiotic, meaning that it is a form of penicillin modified to evade the staph's resistance. Being derived from penicillin, it works the same way, messing with the enzymes assembling peptidoglycan polymer chains inside the bacteria's cell walls. But it is resistant to penicillinase, the enzyme that staph secreted to disable penicillin. Due to those impurities in the early batches of vancomycin, doctors still thought it as toxic, so they set it aside in favor of methicillin and other beta-lactam types like cephalosporins. But even as it became clear that those toxicity issues stem from early impurities, the drug remained a pain to administer for doctors, nurses, and patients alike. Dosing it is tricky. You can't just give them a pill. High doses can be damaging to your hearing and kidneys. And it can cause a non-allergic reaction called red man syndrome by triggering the release of histamines into the body, creating a red rash on the skin like as an allergic reaction, but not quite. So for the next 2 decades or so, vancomycin faded into the background, only occasionally brought out for particularly difficult staph infections. But as methicillin usage boomed throughout the 1960s and 1970s, staph soon became resistant to that too. Quite quickly, actually. It picked up a special gene that replaces the cell wall building enzyme that both penicillin and methicillin targeted, effectively sidestepping both. The first reports of methicillin-resistant staph, shortened to MRSA, emerged in 1961 throughout the United States and Europe. By 1972, 30 to 55% of the staph infections in Zurich hospitals and others were methicillin-resistant. Most troublingly, a minority of these infections were resistant to multiple antibiotics. For this, doctors increasingly realized that only vancomycin can fight these bugs, making it a drug of last resort. MRSA's terrifying rise in the late 1970s brought vancomycin back into the limelight. In several symposia held in late 1978 and early 1979 in Atlanta, San Francisco, and Chicago, the medical community began discussions on bringing vancomycin back into the fray. Papers on the drug's history and mechanism of action against microbes were presented. Studies of the drug's toxicity, the pure form, not the Mississippi Mud version, showed that it caused no systemic toxicity in reasonable doses. New understandings of how the drug spreads through the bloodstream help grant a better understanding of how to avoid negative side effects like kidney damage, though, like I said again, doctors and nurses are not a fan of its natures. After the symposia in 1978, mentions of vancomycin in the literature began to grow very rapidly. Doctors considered it the only uniformly effective treatment for staph infections, the last line of defense. And over the next 15 years, usage of the drug grew rapidly, accelerated by the availability of new oral formulations. This only slowed in the early 1990s with the emergence of the first vancomycin-resistant bacteria. No matter vancomycin's cleverness, it was inevitable that bacteria will evolve a resistance to it. The gene, like the truth, is out there, even if only in the very bacteria that originally produced the drug, and eventually other bacteria will pick up those genes. The first reports of vancomycin-resistant bacteria emerged in France in 1986, not from staph, but another pesky bug called Enterococcus faecium, vancomycin-resistant enterococci, or VRE. VRE is one of 2 different genes, VAN-A or VAN-B, and both change the aforementioned dipeptide diala that vancomycin attaches to diala-D-Lac. This reduces the snugness of the fit by 1,000 times, letting the brick be a brick again. The first report of VRE in the United States occurred in 1987, and between 1989 and 1993, the CDC recorded a 20 times explosion of cases. Before long, VRE became the second most common hospital-acquired infection, and it is notoriously difficult to eradicate once you acquire it. It was a nasty wake-up call for the medical community, and people suddenly realized that even vancomycin, our wondrous drug of last resort, can be defeated. Over time, 8 genes have been identified that convey some form of vancomycin resistance. And once the gene was out there, it seemed inevitable that MRSA would pick it up. Studies in the late 1980s proved that the VAN-A gene can travel on these floating, quote, USB drives for genes, end quote, called plasmids. A plasmid was used to successfully transfer VAN-A to MRSA in the lab, confirming that it can theoretically work. The newspaper headlines screamed doom, but it took some time before doctors actually saw these VAN-A superbugs in the market, 2002, and part of the reason seems to be that vancomycin resistance produces an inferior bug. The VAN-A gene forces the bacteria to maintain a second set of quote-unquote equipment for cell wall construction. The result is excessive energy use plus what seems to be a slightly inferior wall. In the absence of vancomycin, VRSA, as it's called, is easily outcompeted by regular MRSA. As a result, cases of VAN-A-type Versa superbugs remained relatively low. In the 10 years after 2002, just 33 cases of the bug were reported, and most seemed to be due to unusual circumstances where an unfortunate patient with MRSA also happens to have VRE. Ouch. Don't leap for joy just yet. MRSA spontaneously evolved an alternate compromise quote-unquote variant called Visa, or vancomycin intermediate Staphylococcus aureus. This conveys a cheaper form of resistance by thickening the cell wall to trap the drug before it reaches the construction zone. Emerging in the late 1990s, Visa is still susceptible to vancomycin, but it's going to need doses so high that you might as well switch to something else. In 1959, a few years after the drug was released, Kornfeld, the Eli Lilly chemist, wrote a letter to Bo, the missionary, about his contribution to the drug's discovery. Bo had no idea that it was his soil samples that had the drug, but was happy to hear of it. Eli Lilly also donated $1,000 to the missionary group, which they used to build a school. Bo returned from Indonesia in 1960 and seemed to have spent the rest of his life doing good. He never personally earned $1 from the drug he collected, and he passed away in 2006 at the age of 88. A life well lived, and that is all we can ask for. Vancomycin remains in use today, though no longer as the universal drug of last resort. Other drugs like linezolid and daptomycin have sort of taken that role, if it still exists. Meanwhile, researchers have spun out vancomycin variants like telavancin, dalbavancin, and oritavancin, which once again re-enable vancomycin's mechanism of action. Through them, the antibiotic of the ages, nearly 70 years old, lives on. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.